Okay, well, let's go ahead and get started. I'm going to do that and share this. And Renaissance weekend is the top of the morning to you.
Right.
About 300 people there. There were 6 sessions related to AI, lots of sessions related to politics and philosophy and this and that. Met a lot of interesting people from Google and Apple, and didn't see anybody from Microsoft. But have you heard of a company called Cohere?
No.
I mean, I had not either. $5 billion valuation, run by this guy who's 30, and it is essentially ChatGPT for the commercial market. And he has hired people to fill in the gaps so that when you say, ask a medical question, you will get a specifically trained medical answer. And if you ask a financial spreadsheet question, you will get specifically trained.
I see. Okay.
Commercially viable answers. So that's the ticket. Now I've got a number of people who signed up as new members who said they'd be watching the video. So welcome, new members, including a number of people who are interested more specifically in the concept of, if you have a computer with common sense or great intelligence, will it be a conscious entity? And that's, to me, is a fascinating question of philosophy, and I'm happy to talk to various people about that when the time and need arises.
Okay. Yeah. I have a simple metric, which is, I think consciousness is just knowing about yourself, and lots of computers know about themselves. So I don't even think it's an interesting question. I think it's a question of, you don't know what consciousness is. But that's my take on it.
Sure. And my take is, you split the problem in half, that there are a number of behaviors that you exhibit because you're conscious, and you have an internal sensation of being a conscious entity. And we know all about the behaviors, and we can certainly replicate the behaviors. And whatever internal sensation computers might have of themselves, it will be different than whatever humans have of themselves, because your internal sensation is based on your sensory apparatus and your experience with the world and your goals for the world, and whether or not you're achieving your goals, etc. So all of these things will be different for an AI or a computer, and we should expect it to be different.
Not so different. I mean, proprioception, it's an important thing, but Dexter has proprioception. It knows where its joints are. So
exactly, you will have such a sense. That is, the machines will have these senses like vision and hearing and stuff, but their internal sensation of what they see and hear and proprioception will be different, as in, you can look at this green and you see yellow, and I see yellow, and we presume that you and I see yellow the same, but we have absolutely no evidence that we do. We just presume it.
Okay.
And one might presume logically that whatever sensation a computer had of yellow would be different.
I would say, when somebody brings up that topic with regards to AI, it's just a flag that they don't understand, to me. I mean, it's just because consciousness is in common sense, consciousness is extremely ambiguous.
Yes.
But if you understand processes and thinking and all that stuff, it's just like, no, how much memory do you got? Oh, we're running out of memory. We can't remember this stuff anymore. We have to do a garbage collection or whatever,
Yes. Other topics for today, I wanted to give a quick review of neurons and brain simulators and what the UKS is about. And ChatGPT is a source of conditional information. Then we get to the real meaty thing of vision and how your brain might be storing visual information, which is the whole world of fascinating topics. This is another one. And lastly, William's been working on language disambiguation with ChatGPT, and I wanted to share the things that he's been working on, even though he said he couldn't attend today.
Okay, cool.
So, neurons in the brain simulator, quick review. I did Brain Simulator 2 in 2018. I did Brain Simulator 1 in 1985 or 6, and it could simulate an array of about 1,200 neurons. And Brain Simulator 2 can handle 1 billion neurons on a desktop machine. And you play with that for a couple of years and you learn a whole lot about neurons, including things that neurons are really good at and things that neurons are not very good at. One of the things that's really neat is that you get 16 billion neurons in a neocortex. So there is a plethora of switching circuitry available to the neocortex. They're really good at detecting boundaries and differences. They're really bad at being fast. They're ponderously slow relative to a transistor between 100 million and 1 billion times slower. They're partly because of this, they're really bad at handling numerical values, and they're really bad at math.
That's
yeah, well, you can coerce them into doing a little bit of arithmetic, and when you stop to think about it, in second grade, we learn about adding and carrying and stuff like that. That's an algorithm or a technology for adding things. Really, addition is you put this group of things and this group of things together and you count them. Well, that's a little ponderous, but that's what math is really about. And neurons really are very bad at even doing that. There's a lot of talk about neuroplasticity, which is how your brain grows new synapses to store information. And the problem of neuroplasticity is it's great but it takes hours. So it's great at allocating more capabilities to handle certain types of problems that you need to be able to solve. But if you need to create a connection right now, that connection has to already be there with a zero weight, and you can increase its weight in order to create the connection.
Is neuroplasticity another term for learning?
I don't think so. And the reason I don't think so is it is so slow. So learning is you have a connection between objects and words, for example. And if, for example, we wanted to call this for the remainder of the conversation, we'll call this a shoe. Okay? What is it? It's a shoe. It takes one instance of an explanation, and not only do you know that it's a shoe, but you know that it isn't really a shoe. So you've got a whole milieu of information that you created in one shot in less than a second.
Good.
And the only way that could happen is if those synaptic connections were already there waiting to be pressed into service. And so you can reasonably quickly change the weight of an existing synapse, and that's what we'll call learning. And then your brain is going to figure out that, oh, I need some more capacity in this area or that area, and it grows new synapses and may allocate new neurons to that neural capability.
And that takes how long does that take? Does that take years, or what?
Plasticity?
Yeah.
Yes, the growing of new areas. It's more or less continuous, but if you have two neurons that are reasonably close and you want to grow a synapse between them, maybe an hour. If they're further apart, obviously it takes longer.
Okay.
Isn't it also affected by age?
One has to presume, but I don't have any knowledge about that. I mean, I don't have anything factual. Based on my experience with BrainSimulator 2, I started writing BrainSimulator 3. And one of the things that I could do in BrainSimulator 2 is I could build a graph, and a graph being a set of nodes and relationships. And if you presume that that is a reasonable process for storing intelligence information, and I'm going to make the case that it is, that one might estimate that nodes have an equivalent of about 100 neurons, which coincidentally is similar to cortical columns, which have been seen in the neocortex. They're clusters of 100 neurons or so. And so there's some, tangential relationship that might exist there. But if a node takes about 100 neurons to represent, that limits your brain to 160 million nodes of available capability. And when you start to think about, well, what is it that you store in your brain? Maybe you only know 160 million things. Maybe you only know 100 million things. Maybe you know 200 million things. How would we know the difference? And counting these things is a little bit difficult. I want to just mention these things, and then I'll show you. In this graph of nodes and relationships, and the nodes I call things because they have a little more capability than fundamental nodes. We've got attribute inheritance with exceptions. Nodes have relationships to attributes. You can have clauses, so you can have conditional relationships, automatic subclassing, and attribute bubbling. Automatic subclassing, as you discover that there are a number of objects that share a number of attributes, you can assume that they're part of a single class. Attribute bubbling says if you know that various objects are dogs, and all of the dogs have specific attributes, you can bubble those attributes up to higher levels, so dog has the attributes. Mm-hmm. And we've got unlimited relationship types. The benefits of this, it's really fast, much faster than neural networking. It requires a lot less memory and a lot less energy. One-shot learning, automatic inference, and it's explainable. And the graph is married to any number of agents. And I'm going to just jump out here and show you what the graph display is and give you the same demo that I've done before, sort of as a refresher, but really quickly. Good. Fido, here I'm going to add a relationship to this is a display of the UKS content, the Universal Knowledge Store. So if I say Fido is a dog, bingo, there's a relationship that says Fido is a dog. Dog is an unknown thing. We know nothing about dogs, but we know absolutely that Fido is one. We can also say that Spot is a dog. And now Spot becomes a dog.
So at the time you typed it in, the UKS didn't know what Spot was or what dog is.
Yes.
But it did know what ISA is.
Yes. Yes. ISA is hard-coded.
Okay, good.
It's pretty difficult to avoid.
Yeah. But then when you want to add a relationship, you can just type in foo for type. Does that work?
Sure. In fact, I can say dogs have 4 legs. It's created this has.4 relationship type. If we look down in relationship types, we can find it. It's added leg, it's done all of this good stuff. And it knows that the has4 relationship type that it just created is a child of the has relationship.
Oh.
And
oh, that's very interesting. Has4 as a relationship.
Well, you have to shove the 4 somewhere.
Yes, this is a big problem. I've had the ConceptNet has this huge problem here.
Yes. So you can add the 4 anywhere you want, but it makes sense to add it to the has relationship because it's not a property or an attribute of the leg, or it's not an attribute of the dog. It's an attribute of how many the dog has. So I put it on the has relationship, but you can build all these relationships and they happen all the time.
Okay, and so has becomes a sort of a class of relationships, and then there's
Exactly.
subclasses.
Exactly. In the same way you can have Fido and Spot are essentially subclasses of dog.
Okay, and what other things are like has that are pre-built in as meta classes, if you will, for relationships?
I put in these, and these are not necessary. I put in greater than. Has child is a real key. You got to have has child, and has child is the inverse of
is a. Yeah.
And so is-a has a relationship that it is the inverse of has child. And so
yeah, okay. We want to avoid duplication here because I am worried about this, but it is kind of the same thing, and so yeah.
So because of this, if you have a relationship that has an is-a that has an inverse, you never use it. You always use the one which is has child. So throughout the data structure, there's only has child relationships.
That makes actually more sense to me, even though I love the word is-a. I understand why you do that. Good.
Right. I've got a number of properties here.
This is really, Charles, I've struggled over these problems for years. So this is really good that you're unifying this stuff.
And here are some properties that some relationships might have, like is commutative. Is similar to, is commutative.
Good.
And is exclusive is used in determining whether or not relationships collide. That is, you can't have 4 legs and 3 legs simultaneously because numbers have the property of being is exclusive. And if we looked up here under the numbers, we'd find that they have the relationship is exclusive. And there are many things that are exclusive and there are many things that are not. So you can have.
So is exclusive is a property of a node, not
it's a property of it is a property of the relationship. Well, let me say, yes, it is a property of the node in that you cannot have more than one of these nodes, relationships to more than one of these nodes in a place. Does that make any sense?
Well, it does, but has4 has a number in it, so.
Yes, and so you can have 4 legs and 2 eyes, and that's okay, but you can't have 4 legs and 3 legs.
Yeah, you could have 4 legs and 4 eyes.
You could.
Yeah.
Yep. That's it for the pre-built.
Oh, I see. You can't have 4 legs and 3 legs.
Yes.
So it's the relationship including the target of the relationship.
Exactly.
It's the combination of the relationship and the target of the relationship are exclusive.
Exactly. So if I were, for example, to look at the properties of Fido, and I turn off my breakpoint, the only property that Fido has is Fido has 4 legs. And if we turn on the complete relationship display, you'll say that Fido has 4 legs because he inherited the property from dog. Okay, now we'll say Tripper. Tripper is a dog. And we'll say, look at the properties of Tripper, and he inherits the same property. Tripper has 4 legs, but if I say Tripper has 3 legs, now if I look at the properties of Tripper, it broke. Anyhow, this overriding, the Tripper has 3 legs when I'm in the main branch, overrides this, and you will only see
there would be an
Tripper has 3
exception.
legs.
Effectively, yes.
Okay, but it needs the is exclusive property in order to be able to do that calculation.
Excellent. Okay, now is it possible to have a relationship of has 4 legs whose target would be a Boolean?
Can you give me an example of why you would want such a thing?
Fido has 4 legs. True. It's an assertion. Fido has 4 legs. True. But no, Fido was in a car accident. He only has 3 legs now, had to change.
Right. Let us go to conditionals. And we'll say dogs can play fetch if weather is sunny. And now under dog, you get this property. And if we again look at the query, we'll find out that the dog can play fetch. And let's go to back to Fido so we get less. Fido can play fetch. And the reason that Fido can play fetch is that the weather is sunny, which it defaults to whenever you enter the conditional. It assumes the conditional is true. But if we say weather is not sunny, weather is not sunny, and we do a query, now you can no longer play fetch with Fido because the weather is not sunny, and you can only play fetch if the weather is sunny. So
is kind of one of these meta relationships, just like has.
I am in the process, when I worked on vision, and I'll show you this in a moment, working on using the relationship type has attribute.
Yes.
And that is a much more concrete. These things like is and has, they're, has in English means that you own it or you have it as an attribute or something. And so I'm trying to get the relationship types a little more concrete. And as as William's project disambiguation progresses, that that will become a little clearer. So, any more questions on?
Well, is not and is. So what have we got? Weather is not sunny. Supposing we had a relationship, weather is sunny. Now we have a contradiction between these two relationships.
No, because if I say weather is sunny, it replaces that relationship, because not is one of these exclusive things. You can't be both not and not at the same time.
Yes, okay.
And so when you add these relationships, it works with weights, and so and I don't recall exactly what the practicality of it is, but of course you can be red and green at the same time. That's perfectly okay, but one has to presume that you can have any number of properties that you can have multiples of at the same time. But and it works by, let's see what the weights are here. So it sets a 90% weight if it were when it's essentially sure. But if we said Fido is black and Fido is white, and we go look at where Fido was, and now because colors are not exclusive, he can be both black and white simultaneously. And
okay, good. And you also have this notion of kind of like, if you say something is something, let's give it a 90%, nothing is certain in the world. Is that what you're doing?
Well, actually, on this dialog box, you can set the confidence level to whatever you want.
Oh, okay. Well, but I'm saying a common sense.
But it defaults to 90.
Good. That's what I want to say. This is an important principle. Common sense, when you say, I have $100, what do you really mean? Well, last time I checked my wallet, I have $100, but it might have fallen out and blah, blah. And, no assertion is certain. But common sense wise, we say, let's just presume that this is right and not question it, because it takes so much energy to keep questioning everything all the time, that would just say, yeah, let's go with it. And some, major, asteroid hits, then I no longer have $100. That's okay.
Right. Exactly. And so I presume
I'm very happy you're doing this.
I start off with a 90% confidence.
Good.
And there are some things that are 100% confident. But essentially they're things I code in.
Yes.
So that's all I wanted to say about the structure of this system. And now the questions are, well, how are you getting data into it to make it actually useful? And going back to this picture, William wrote first he wrote a system that would take a list of words and get data from ChatGPT and build this knowledge store. And it works reasonably well in some circumstances and less well in other circumstances. And circumstances, it works much better with nouns than it does with anything else. And to that end, I have a couple of word lists of nouns that any kindergartner should know, nouns that any first grader should know, on up to sixth graders. And you can download this and try it out and see if it works. I wanted to get a little more exercise for clauses, because the clause that I showed you with it is essentially the only testing that's gotten. And so William wrote a thing that, given some nouns, you can say that I think his syntax is a noun can something if something is something. And ChatGPT will dutifully return things like do this, like of this form. And some of them make sense and some of them don't make sense. For example, you put in the word type and it says keyboard can type if finger presses button.
Oh.
Now, this is a true statement, but not particularly useful for this instance.
Yeah, I'm less concerned about, whether ChatGPT is good or not, and the basic structure of this UKS and what you're developing. And I want to make an observation of this. A is B if C is D is a kind of a non-programmer thing to say. A programmer would say, if C is D, A is B.
Yes.
Right. And so you've done that in your third line of the slide. So I think I like that form better, just because
here's why
I'm a programmer, and
here's why it is the way it is. Because A is B is a relationship.
Yes.
And C is D is a relationship.
Yes.
And you have a conjunction that joins two relationships, or any number of relationships in the data structure. And the conjunction can be anything you want.
Yeah. Oh, I see. I was thinking very specifically.
Conditional.
A is B is the main thing you're thinking of, and C is D is this little side thing that might affect it. But now I see they're really the same, any relationship. Yes, joined by an if. Excellent.
Right. And an example that I've used already is that Mary went to the store with Sally. Well, that is Mary went to the store is one relationship. Sally went to the store is another relationship. And with means that these two relationships are joined, happened at the same time or something or other.
Okay. Yeah. I guess in English, if we're going to your second line on the slide, you'd say, if A is B, then C is D.
Yes.
Yeah. Okay.
Correct. But back at the data structure, because this is a relationship of dog, leading off with weather is sunny is kind of backwards to the way the data structure has to be built, because this has to be a relationship owned by dog.
Yeah. No, this is all making great sense.
Yeah. Okay. So we don't want to do that. We want to do back to this screen. And next topic is graphics or vision. There are a bunch of processing steps in vision. And let's imagine that your visual cortex has about 1 billion neurons. And so let's ask ourselves, how can all of this work in about 1 billion neurons? And can we stuff all of these processing steps in there? And the answer, of course, is obviously you can, because it seems to work.
Sometimes.
But there are a bunch of processing steps, and I have got a bunch of UKS things that live with them. There's boundary detection, and boundary detection is typically done by a convolutional setup. And I chose to write something different because I ran into a number of shortcomings in convolution. For example, if you have a patterned area, so you can say in this area the signal is going, the brightness is going up and down, and then there's a boundary where it starts to go up and down at a different level. You want to be able to detect that boundary, and convolution is very bad at that. So
how does boundary detection deal with stuff like gradients, where there isn't really a clear boundary, but it sort of fades from one color into another?
An excellent question, because when you look at the individual pixels of a JPEG, one of the ways that compression happens is that the boundaries all get softened. And so a real boundary might go across 4 or 5 pixels. And you never get the abrupt boundary that we humans think we see. It's always kind of faded in, and yet your mind is able to turn that into a very abrupt boundary. And then you ask the opposite question, which is, how do you handle a gradient? And the answer is you have to ignore the gradient. When you are looking at a white wall, for example, it is a completely different shade of white at one side than it is at the other. And yet you detect no boundary. Unfortunately, JPEG does detect these boundaries, and so if you don't have a lot of shades available, you see all of these abrupt areas of beautiful shading that happen between the boundaries. Did that answer your question?
Yeah, that makes sense.
And so I am deliberately hiding the actual boundaries, and that's one of the things. Another thing that convolution actually can solve that problem pretty well. So you find the boundaries. Now you want to find line segments within these boundaries, and you'd also like to be able to find arcs, but I haven't implemented that. And line boundaries, there is a published algorithm called Huff, and I will show you that in a moment. But now we want to find line segments.
Charles, just back up a second. Looking at this white wall, one of the things we could say is all the RGB values that are within this range, we're going to call them white.
Yeah.
We could say something like that. But
you can't.
But you can't. And you probably have seen these optical illusion things where a literally color that matches that white is really considered to be black because of the surrounding shadows or whatever.
Exactly. It all works with deltas.
Yes.
And so my homebrew algorithm shoots rays through the image. And then with that ray of these values, you can apply whatever complexity you want to the ray to determine where there might be boundary points in that ray. So you can compensate. I mean, essentially, you can take the first order derivative or the second order derivative, or you can do whatever you want, and you can ignore changes in. And I work, by the way, rather than RGB, I work in HSL.
Yes.
Because if you find an abrupt boundary of luminance, it's a boundary. If you find an abrupt boundary in hue, it's a boundary. Anywhere where you find an abrupt boundary, it's a boundary. But now you get to have different parameters for all of the others. So
Okay.
boundary detection.
This is tough. This is a tough problem. Great.
It is a tough problem, and a problem that is really not yet solved. And it is what is keeping us from having self-driving cars, as an example.
Wow.
That the vision isn't good enough. You can use LiDAR or something to know where all of the surrounding vehicles are, and that works. And they use LiDAR because, again, the vision's not good enough. But you can't read the highway signs unless you have different reasonably good vision. And a lot of things like pedestrians and dogs don't show up that well in the LiDAR. So you have to have good vision, and it simply doesn't work well enough to be used in areas other than highways. And yeah, it sort of works around town. It's very impressive, but it's the vision that's the real hang-up.
Mm-hmm.
Okay, now we find the lines, and then we have to find the segments. And then we get to the real key, which is to find the corners. If you can find the corners of an object, you can pretty well define what the shape is. And if you know what the shape is, you have a pretty good idea what the thing is. And then eventually you'll get third dimension of distance estimation. But when you think about how your eye works, well, the retina is a two-dimensional sensor. And so the fact that you see in 3 dimensions is entirely a projection. And and I like, rather than talk about binocular stuff, I'd rather say, well, you can see the depth in a photograph, no problem. And there's no binocular depth cue in the photograph. So we're going to look at what other depth cues there are.
Good.
Okay, UKS things, and we'll blast through these because I'll show them to you. Corners, distances, corners and distances. To me, a corner is an angle, and an angle you can define with 3 points, and by merest coincidence, you can define an arc by 3 points. So when I implement arcs, it may work that way. Distances, I've taken a unique approach to representing distances and colors and outlines. And now we have a collection of current shapes. These are the things you can currently see. Then there are stored shapes. These are the things you know as and can identify as shapes. And finally, there's a mental model into which all of the things you can see get stuffed. And with those, you can decide what you see, and you have this mental model so that, and this is really important because your high resolution visual field is very small. And so you have to be able to identify the object in this direction and know what it is and put it in your mental model. And then you move your eye to identify the object in this direction, and you have to remember what the previous object was. So you have to remember how these things all work, and that happens in what I call the mental model.
Yeah, Charles, so the process of matching a current shape to a stored shape is an important one here.
I will show you it.
Excellent. Okay, that's what I want to see. Yeah.
Okay. So we're going to change to a different network with some different stuff in it. Maybe it's in the recent list. Yes, vision test. No. Here's the UKS. I've had it open up to stored shapes. The only stored shape we know about is a square.
Okay.
I'm going to open a file, and we can imagine that this file is a single frame of a stream that's coming in from an eye. And here we have a square, and here it is identified what it is, and its current shape 0, and it's a square. It has a confidence of 1, It has a size of 4, it has a color of 12, and an orientation of 0. And over here is the mental model. So if we open a different square, it's going to be still a square, but now it has an orientation of 30 degrees. This will go dim, the mental model will go dim after 10 seconds. While it was bright, it was showing you what it had recently seen. Now it is showing you what it remembers. And so it remembers that this is a square, and over here in stored shape, we can look at what is inside a square by expanding this. And a square contains these parameters. You go a distance of 1, you turn 90 degrees, and I can make that bigger. You turn 90 degrees, you go a distance of 1, you turn 90 degrees. You go a distance of 1, you turn 90 degrees, and you go a distance of 1 and turn 90 degrees. Pretty well the definition of what is a square.
Wow. That's like logo. That's a process. It's really a process you're representing.
And what I like about this is that you can do anything with it. And what I don't like about it is that it's kind of serial. And you seem to be able to know what a square is in parallel. And I don't have a good answer to this, but this has the capacity of working.
You know what I mean when I say it's like logo, the programming language.
Yes,
logo?
yes. With the turtle.
Yeah.
Yeah. Okay, now we're going to make it a little harder by showing this rectangle. And you say, aha, it's recognized as a square. It's doing a closest match. It's only got a 75% confidence. But if you only know one shape, everything looks like that shape. And oh, by the way, after the 10-second delay, what you remember seeing there is a square, because it's all you know. And so what we're going to do is do a little refresh, and then I'm going to say, no, that's not a square. So I say refresh, and I say no. And what has happened is it's created a new stored shape. And I'm just going to, for my convenience, rename that stored shape. Now, if I do a refresh, it has found that this is a rectangle, and it's got a confidence of 1. I can now open this other rectangle, and it has a confidence of 1. And now I can open this rectangle on an angle, and it has a confidence of 0.888, not because it's on an angle, but because it has a different aspect ratio.
Yes.
And this, the stored rectangle is 1 by 0.6.
Yes.
But the key is with these stored shapes, it can recognize them anywhere in the visual field at any angle, orientation, at any size. And the way it works is, here's the processing of your visual cortex. And I'll turn some of these on and off, where this is the raw image coming in from the eyeball. Here is its processed boundaries. Here are the lines that it's found with the Huff algorithm. And we'll talk about some of the irritants of the Huff algorithm. But eventually it says those must be the segments because they're the highest likelihood. And these are the corners. So the good news is that it's found 4 corners, and it knows that there's a rectangle. And if we come over here to a slightly more complicated image, like this, it says it's found all the corners, and it says, aha, there's a rectangle, a square, and a rectangle. And the two rectangles are, one is at size 4 and one is at size 5. And so it can find multiple objects. I have not addressed occlusion, but it is doing a closest match. So it will find the best match that it can.
Yeah,
So,
Charles,
yes.
Early, about 2 minutes ago, I detected almost kind of like a supervised learning thing where you said, this is not a square. You clicked a button and said, this is not a square. And then it said, oh, I got to make something new. And now you got to name it. So that's kind of like what is it? You as God are interceding in the system and say, nope, you're wrong. So,
right. And I can easily see that as soon as I have ARCs running, I should be able to use a database of handwritten digits and train it up and see how this mechanism compares with the various neural network mechanisms on the MNIST database, for example.
Yeah, I've been doing a lot with programming by example lately, and
Yeah.
it occurs to me that this is kind of analogous to programming by example, because you're literally looking at something as it's coming in. You're not fabricating, it's coming in, and then you're making a call, and then you're remembering that, and then that's a kind of programming. You're remembering what your call is in a way that you can utilize it later. Yeah.
Exactly. And so if I tell you you're wrong, I have to also tell you what the right answer is.
Or it's good, yes, or
But
tell them it's a different answer, yeah.
But if I don't tell you what the right answer is, you'll just call it a stored shape.
Or a square with a low confidence, that's
right.
okay.
And
yeah,
if we look at current shape, these are the 4 shapes that it can currently see.
Yes.
And if we expand them, they have shapes which are stored shapes. And here I'm using has attribute. It has attribute of a color and a size and a position in the mental model and a rotation in the mental model. And it's a shape, and the offset is an added complexity that's necessary for this mechanism to work, but we don't have to do it if you don't want to. And you can see this is all the information that you need to resurrect this image in your mind.
Welcome to the Rusted Garden Homestead, and today's 2-minute tip.
Zaid, were you saying something?
If you want to pick them when they look something like this. Dark green.
Your microphone is screwed up.
All the way down.
Yeah.
As soon as they start turning more yellow, they're past their prime. They're not going to grow any longer or bigger. They're just getting
cool.
fatter. The seeds are going to develop. Pick them when they look something like that.
Okay, so I was wondering, so I noticed that the system essentially it has to pick from a shape that it already has seen, but it doesn't have the option to say, oh, this is an unknown shape I haven't seen before.
Essentially that's what happens when you say no. It says, no. The way it's written is there's no threshold, so it will always think it's something with a low confidence. But if I said, I could set a confidence threshold that at below a certain confidence, this is something that's entirely unknown. But in general, it doesn't make any sense to store that. We could invent that it's an unknown shape of some character, but the alternative is as you turn on your camera, the first thing it does is try to make shapes out of absolutely everything it sees. And that doesn't make any sense either.
Yeah, that makes sense, I guess.
Well, yeah, so we have to come up with a difference.
I do like this unknown category, because you see a weird animal once, you say, that's a weird animal. I don't know what it is, but I remember I saw a weird animal. Then you see the weird animal again, and you think, gee, maybe this is a really, important case, and I ought to make up, a name for this. And
well, let's pick up this thing. You don't have a name for it either, but it thinks it's a rectangle, but with a confidence of 0.25. So I could say that any confidence below some value is just unknown.
good.
But I haven't done that.
Good.
But you can also see that, well, once that image is quit, what you remember seeing is there's a rectangle in there, because that's the only choice you got.
Mm.
Yeah, that's interesting, because when I see objects that I haven't seen before, I tend to remember them as I saw them rather than with the shapes that I already know.
Yes, but you have to really think about it. And you have to want to remember something in order to remember an unknown shape, because your vision is mostly clutter. And if you want to remember something, you got to really pay attention to it and want to. And that's why I've put in the no button. And then you can remember it without any trouble. Then you'll remember what you saw instead of what you thought you saw.
What did you say? Your vision is mostly clutter?
Yes, that you look around. I mean, you're looking at this screen and you can see a couple of characters at a time, and the rest of it is mostly noise that may get your attention, and then you look at that area.
Okay.
And most of what, I mean, and the same is true if you think about hearing. The key is to be able to hear the meaning coming in out of the audible clutter at the same, it's exactly the same problem. You have to get the signal from the noise, and vision is incredibly noisy. I did want to say, no, I didn't need to talk about that. What I did want to talk about is going through the algorithm a little more in detail. And that's not how to do it. You got to do it by pressing this button. And refresh. And we'll go back to a square because it's something we understand. Or a triangle if you like. Yeah, triangle. Why not? There's a triangle. So what I want to do is we'll turn off the segments, and you can see the lines that the system has picked up. And I'm going to show you what the Huff array is. And essentially, each pixel in this image represents a line. And so as we mouse over them, you can see the lines, and the color is proportional to the number of hits that line has. And it's at the very bottom of the screen. I don't know if you can see it says 66 votes. In white text.
Oh.
Yeah.
It's tiny. Yes, I can see that.
Yes. Well, it's for debug purposes only. But as I move away from the center of the line, from the center of this whitish area, this one's got 17 votes, and this one's got 20 votes. And so the key is to be able to ascertain which of these things are relevant. And here we can see is this line, but you can see there's an outlier white pixel. I can zoom this in, by the way. And this outlier white pixel
Yes.
It's got 22 votes, and it corresponds to this oddball line. It corresponds to this oddball line that you wonder what it's doing there. And the reason this shows up one of the shortcomings of the Huff algorithm. Well, these lines are picked up with an algorithm that simply does a local maximum. And the problem is this blue line, you can see it picks up a couple of votes as it comes through this boundary, and it picks up a couple of more votes as it comes up through this boundary. And because of the way it crosses the boundaries, it can pick up more or fewer votes and actually create a little local maximum for itself where none ought to exist. And to that end, I don't just count votes. I count where the points are. So in the next iteration, I'll be able to say they have to be contiguous votes. Discontiguous votes don't count. And then a lot of this noise will go away.
Outliers, yeah.
Yeah, but I also wanted to show you some more complicated stuff and give you a better picture of what this algorithm is doing. Let's pick up 3 squares. Okay, it has picked up very few oddball lines, and you can see the oddball lines come based on where the line happens to hit coming through the boundaries. Because this one comes in between a couple of pixels, it gets credit for hitting both of them. And then it hits 2 more here and 2 more there. And that might be, yes, this bright dot here is one of these oddballs. But now you can see here are the, oops. Here are the vertical lines across the top, these specks. And you can begin to get an idea that moving horizontally is the distance from the origin. And so if I pick this one, it's furthest from the origin. And moving vertically is the angle. So as I come down here, I'm going to pick up this angle. And you can see in this center, I pick up that line. And over here, I pick up this line. And so they're down here are these verticals at the other end. And so one of the shortcomings is that Huff doesn't pay attention to discontiguous lines, although I'm prepared to do that. And one of the problems, by the way, that I see in most AI systems that do vision is that you get a bunch of errors in the first stages of processing, and then you spend the rest of the stages trying to get rid of the errors. And I am looking for ways to not get the errors in the first place. Now, I should point out that the Huff algorithm has nothing to do with the way your brain might do this. It is mathematically intensive, but is blindingly fast because of the way it counts the votes. And another general problem of AI is that it is tremendously obsessed with performance, where sometimes the way your brain clearly does it is, well, if you have 1 billion neurons, you can have a neuron that corresponds to every possible corner on your visual field and every possible line on your visual field and every possible arc on your visual field, and you'd still have 750 million left over to do some of the processing. But another problem that you have is that at the top of the screen, I actually can hit the point. There we go. At the top of the screen, you see a near vertical line, and at the bottom of the screen, you see another near vertical line. Oops. I want to find the same vertical line. There we go. And you can see that these lines are seriously offset from another. So although this is line angle from top to bottom, it does not wrap, because the distance from the origin is the negative of what it was before. And it would sure have been nice if some mathematically inclined person could set this up so it would wrap. It would be much easier to find local maximums if the array wrapped the way it should. And so I've shown you what corners look like. Let me show you what curves look like. There's a curve. Let's turn off the lines because they make absolutely no sense in this context. And the corners, they don't make any sense. Okay, so this is a curve. And if we trace along here, one would think that with this transform, we should be able to find arcs really easily. But it would be even better if instead of having this oddball shape, which doesn't make any sense to me, it looks a little like a sine wave, but you notice that this area is a lot more curved than this area. So it has to do with the distance of the line from the origin. And this represents 180 degrees. So this curve is one half of the arc, and this curve is going to be the bottom half. And if we could figure out a way to change the transform a little bit so that these, and I should point out that as I started to write arcs, I thought that there should be a way to make this work. And so I wrote this visualization thing because I couldn't not figure out how to make this better than it was. And now I have a lot better picture of how to make this run. And again, we have specks of discontinuity. So if we bring up a image which is a combination of an arc and a straight line or two or three, it's pretty easy to find the straight lines. There's a straight line. There's a straight line. And up at this edge, there are straight lines. So that's pretty easy. And then you get these beautiful sweeps that represent the arcs. And then you have all of this nonsense that I'll filter out when I start looking at requirement for continuity. So once you have corners, you do a simple search of matching. There's one other thing I need to say. Because neurons are bad at storing values, let's go back to this picture, and we'll say angle. We're not going to say angle. Why isn't it showing me the angles? There are distances. It only stores 10 distances. And if we do an expand all, we find that distance 1 is similar to distance 2 with a value of 0.8. And distance 0.2 is similar to distance 0.1 and 0.3 with 0.8. And so when it does matches with angles and distances, it follows the is similar to paths, but since the weights multiply as you go down the route, as things get further away from a perfect match, they get lower and lower confidence values.
Very good.
And where did I put angle? Let's go back to our square. Angle, let's look at angle 90, and then we can get its parent, and I'll know why I typed it wrong. Angle 90, and its parent is rotation. Oh, who would have thought? So the way the system works is I mean, this is a parameter easy to fix, but it is in 10-degree increments. Angles are all in 10-degree increments. I could have made it 1-degree increments, but my suspicion is that we humans are not particularly good at knowing differences of angles that are very small.
True.
If we see two lines that are right next to each other and we can see that they're getting closer together, that we can see. But a line up here and a line up here that differ by 10 degrees, the parallax of your eye probably is greater than that.
Yeah.
And so I picked 10 degrees out of the air as my increment. And so the way the matching works is it takes the values that it gets, and the reason I did this is for neural plausibility. Since neurons are so bad at storing values, you pretty much have to have a separate neuron for every different value you want to store. And then you can say these values are near each other. Well, in your brain, maybe they're near each other because there's physical proximity, but in the UKS, near means there's some sort of a relationship of nearness. And so that's how that is represented. And the search is a closest match search that is the same closest match search that you use if you're saying what has 4 legs and a tail. So you can say what has 3 right angles, for example. Well, that is probably going to be a square.
Because you're missing just one of the angles. It's occluded.
Exactly. But I haven't done occlusions and other things, but they should work tolerably well. We'll find out in the next coming weeks.
Charles,
Okay.
when you look at a square and you look at it off angle, it could look like a trapezoid.
Exactly.
Right. So how do you manage that? This is more a 3-dimensional vision kind of question.
2 things. The first is, well, backing up a square, even squares are exceedingly uncommon in nature.
In real life, that's true. Yes.
And so the shape cue for distance isn't as good as some others. And one of the distance cues that I haven't written is brightness. And the shading that Zaid talked about half an hour ago is a really important cue for 3-dimensional depth.
Yes.
Because you know right off the bat that things shade darker as they get away from you, get further away from you, or they lose their, in the distance, they lose their saturation. And all of the colors become grayer because air is generally hazy.
Oh, Okay.
But something that is really only lightly pursued is that if you want to know how far away are the things relatively near you, you move your head a little bit. And everything moves in absolute proportion to its distance away from you.
Yes.
And that is the cue that I am going to be thinking of as the most important. That from frame to frame, you can see all of these relative motions.
Yeah, with one eye, you can get stereo vision by taking 2 snapshots of moving your head. So it's...
Yes. And your retina seems to be capable of detecting moving objects and how far they move. And so you'll know right off the bat, if you move a little bit, that everything moves some distance in the same direction in proportion to its distance away.
Okay.
You know, I think I think our eyes.
Yeah, go ahead, Zai.
Yeah. I heard that they move a little bit, but we don't perceive it. So, just tiny movements that help with stuff like perceiving distance.
Yeah, moving your eye.
So I mean, even if they're looking straight ahead, they're kind of moving or jittering slightly.
Yes.
There's an optical illusion that kind of shows it.
That's a very good point, because if you think about a viewpoint with an axis of rotation, if you rotate only around your axis of rotation, everything moves laterally exactly the same amount. But when you move your eye, you're not rotating your eye about its visual axis of rotation. It's somewhat either in front or in back. And so you still get a visual cue, a depth cue, from rotating your eye as you do from rotating your head. And your eye moves around a bunch all the time. And because as I mentioned earlier, your area of visual high acuity is really small. It's about the size of your thumbnail at arm's length. And so everything that you see that makes you think you can see more than that is because your eye moves around so much. And you remember what you saw. I mean, that's what the ophthalmologists tell me, by the way, that. And just off to the side, your area of high resolution image is likely less than 1 million pixels.
We're talking fovea here. Use the word fovea.
Exactly. Fovea less than
less
1 million,
than 1 million pixels. Very interesting.
And so here I've got a mental model which is 25 by 25 pixels. And I will stick with that resolution till it runs out of steam. But the resolution of your mind is not high def. It is much more likely to be closer to 100 by 100, and probably wider than it is tall. So, 200 by 100. And what that means, the impact on computation is huge, because
wait a minute, 100 by 100 is 10,000 pixels.
Yes.
So how does that square with 1 million pixels?
Maybe it's 500 by 100, and you'll get yourself to,
Yeah. Okay. All right.
I mean, maybe it's more, and I don't recall from the numbers whether that was pixels or cones. So you get to divide by 3 right off the bat.
Yeah.
But the key is that the resolution with which you actually have to do the processing is not nearly as great as taking data from a 4K camera in real time and trying to figure out what's in the picture.
Right.
That's a lot bigger problem than what your brain does.
Right.
Any more conversation about vision, and we'll go on to ambiguity.
I do have a meeting coming up, but it hasn't arrived yet. So I might have to go at a moment's notice, but this is fascinating, Charles.
Okay,
so
well, let's go
please.
quick.
Go ahead.
Ambiguity. The way we're going to solve the ambiguity question is we have a UKS tree of objects, or actions or attributes, which is totally abstract. And also within the UKS, there's going to be a tree of words and phrases. And some of these words and phrases are compounds. So you get the word ball, which is a word in English, and you can have multiple trees for different languages. So you can have language 2, and you can have tennis, and you can have likely combinations like tennis ball, which make your compound words. And all of these are married by a relationship type I'm going to call means. So ball means sphere, or ball means sports equipment. And ball doesn't mean tennis ball, but the phrase tennis ball means tennis ball, but the word tennis only means the sport by itself. So you get to have all of this mix and match combination. And of course, all relationships are reverse parsable. So given that you're thinking about a ball, I could give you the word for it in any language that you happen to know, because you've thought about an abstract of a ball. And maybe the weight of the means relationship corresponds to its usage frequency, which is sort of like its likelihood. And once we have all of these words over here and all of these means relationships, you could see that the system would all still work if we stripped all of the labels off of these objects. You
Charles,
would find out what they
I
were.
love this concept of a means relationship, but is it one directional, meaning on the left side we've got a term and on the right side we've got a, I don't know, concept, but you can't say sphere means ball, but you can say ball mean, does ball mean sphere imply that sphere means ball? That's my question to you.
Yes, you could say the sun is a ball. That's a perfectly legitimate but not scientific way of expressing it in English.
Well, would you know what I'm asking here?
Yes, and this is a problem that
because in a definition, I care a lot about definitions, right? Now I say that there's a term and there's a meaning.
Yes.
And I don't say, and I can't swap term and meaning for each other. It's a one-dimensional relationship.
Yes, and you bring up a point that we ran into yesterday, that although we can ask GPT for the multiple meanings of words and presume that the multiple meanings relate to abstract meanings,
okay,
running them in reverse didn't seem to work very well. So we'll have to spend some time. And if you have an answer,
but maybe that's a good thing that it didn't work.
Yeah.
That has to do with the definition of means and what do you really mean by this relationship?
Yes.
Which is fine. Okay, yeah. Oh man, this is great stuff.
And what it led me to think about is, what are the attributes of words? And I thought of part of speech, and I don't know. I mean, think of the part of speech in terms of a 5-year-old. They don't know about verbs and nouns, but they know that there are things and there are actions and there are
Yes.
descriptors without knowing adjectives, verbs, and nouns. So you would have the part of speech. English is terrible about compounds, and I had to look up to find out what closed, hyphenate, and open compounds were. So basketball is a closed compound. Hyphenates have hyphens, and tennis ball is an open compound. Tennis ball means one specific thing, even though it's multiple words. In your brain, you remember the spelling of lots of words if they're oddball, and we can stuff that into the label of our thing. But something that we aren't storing that would be really handy to have is the pronunciation. And we can get phonetic alphabet pronunciations pretty easily. And by using my similar mechanism, I could tell you what words rhymed with what other words given the pronunciations.
Good.
That might be handy. And then I said, well, what are the likely preceding and following words? And I said that after I wrote that, I just said, well, now I'm rewriting GPT.
Yes, yes, I was just going to say.
GPT in a graph.
Yes.
And Williams got down the mechanisms for you can ask GPT a question and and phrase it in a way that it is parsable results that you can shove into the graph. He's pretty well got that down. So if you want to ask, what are the multiple meanings of this? He can parse that. If you want to ask, what's the pronunciation of this? He hasn't done that, but I'm sure he could in moments. And the same is true if we went to multiple languages. But I don't see words as falling into such a great hierarchy, except maybe by their pronunciation, words that start with this or that. I haven't thought of anything because they're all just words.
Well, no, there's contexts, and a context often is used to disambiguate two different meanings. Oh, when we're in this context, it means this thing, when we're in another context, it means another thing. So the context can form a kind of a hierarchy.
Yeah, and one of the things that you need to do is when you find out that ball refers to an abstract object named ball, which is a piece of sports equipment, you want to essentially be thinking in terms of when you say something is a something, does that mean that it is a different instance of the same something with the same label, or is it a multiple parentage?
Well, there's where your relationship means come in, I think.
Yeah.
Means is different than although.
Absolutely. We tried using is a relationships, and that didn't work with beans.
Yeah, but is often the essential part of a meaning. I mean, I would do a lot of work on definitions, A ball is a sphere that's used in sports, for example. Yeah.
Yeah, and it's not a formal dance party.
Well, okay, that's a different, it is, but that's a different context.
Exactly. So anyhow, we've just scratched the surface on this, and William wrote the first cut at this over the last 3 days. And what's, of course, like all of the things that don't work well are at least as instructive as the things that do. And but I'm hopeful that over the next month to the next meeting that we'll have a lot of progress on this.
I have another trick you can use with ChatGPT, and I'm doing it, Charles. We can talk more about it. Is ask for
Go
the
ahead.
embedding of a word or a phrase. Do you know this word embedding?
No.
Okay, embedding is an array of numbers that is in some sense the definition or the meaning that ChatGPT thinks something is. So it's like 100 numbers or something like that. And you can take any single word or any phrase and ask for the embedding. And then you can take two different phrases and ask for their embeddings. And there's a mathematical comparison between these vectors that gives you a similarity score between the two things. So I have this in DDE. We can talk more about it, but it's useful to say, what is the similarity of this with that? And you get a number out. And then there's tricks that you can do with this similarity to verify whether GPT is consistent with itself. Okay. So this hallucination is a problem, right?
Yeah.
But if we can say that GPT is consistent with itself, like you say, two sentences that a normal English person would say mean the same thing. Okay.
Yeah.
But you can imagine if you're just doing these word sequences and stuff, GPT could have no idea that they're related to each other, right? Absolutely none, right? However, if
Right.
you take those two sentences that a human would say means the same thing, and then you ask for their embeddings, and then you do a similarity between their embeddings, and they are similar, then you feel like GPT is giving you accurate information. But if they're not similar, then you feel like, oh, it was just an anomaly of some word sequences that had nothing to do with meaning, and therefore I should ignore this thing. It's a hallucination. So I've done a little bit of work on this, and I give away everything. So so this is a way in which we can use ChatGPT to validate itself. Literally the same model, really, because the models can be fragile by the fact that, it just so happens that this word, sequence came out and I'm giving you this. But when we replace the words in that sentence with synonyms that you and I would consider synonyms, it should give us the same result and it should be similar to the first thing. We can now use ChatGPT with embeddings to get a numerical score on a similarity. And I loved your is similar to relationship, by the way. I like the word similar. And so then that can help us get value out of this flaky beast of LLMs.
Yeah. Well, one of the things that I talked about over the weekend is that your conversation about internal consistency is a good one, but when I look at hallucination, I look at GPT makes up everything. It's just because it's trained on what we think is
people
correct.
Make up everything, I don't want to get.
Yeah, but the problem that you run into is when you define what is true. To me, what is true is words that correspond to my perception of reality.
Okay.
GPT, no perception of reality. True and false don't particularly have any meaning at all.
Yeah.
And so it's just making stuff up. And if you're like Voldemort and say, tell the truth, well, it always thinks it's telling the truth. It just doesn't know the difference.
That's one of its problems. But if you can check internal consistency, that can help. And maybe what GPT is useful for is just giving you an idea that might or might not be true, and then you verify that with the real stuff like you're talking about reasoning and UKS and all of that.
Okay, I've got a number of other meetings scheduled. I'll send out emails on them. They're coming up in essentially through the summer. I don't expect a lot of people to be coming in, but I'm going to run an August meeting and a September meeting, partly because that gives me the discipline to actually write some code and get some stuff to work and talk to people and make things and make some progress. And so I'll send out notices on upcoming meetings. Zaid, do you have any final questions, comments?
I guess the only comment I would have is that your ambiguity system seems focused on language, but there's a lot of ambiguity, for example, in vision. Like there are certain images where if you look at it, it looks like a duck, but if you look at it in a different way, it looks like a rabbit, with long ears.
Yeah.
Yes, that's an excellent point. That essential and a way to look at that is obviously your vision system is continuously resolving ambiguity, and particularly in 3 dimensions. Everything you see is ambiguous, but your vision system is continuously pulling that together. And maybe we could use some of those techniques in language as well, because human brains are efficient in reusing the same idea in multiple areas. So maybe it works exactly the same way.
That's an analogy.
Yeah.
And the same thing with you moving your head can use your vision detectors, just like an object that itself is moving when your head is static. They could use some of the same mechanism there.
Yes. Yes. In fact, I wrote I did a video on as you move, for example, you can determine what your motion is based on the motion of the objects you see. And by assuming that most of what you see is not moving, you can easily determine the objects that are moving because they don't fit the formula.
Yes, this is perfect and very important. And people are so good at that.
Yes. And
subconsciously.
Even and it's one of these things that 3-year-olds are good at. And you didn't have to spend 20 years of your life learning how to do it.
Right.
Okay, well, on that happy note, I'll wish you all farewell, and we'll
Thanks
be back
so much, Charles.
It's
been a delight as always. I will send you some email when I have some time, but wonderful work. Really great.
Thank
program.
you. Hey, it's really rewarding to actually make some progress on this stuff, and pretty soon we'll have some pieces of it that are working well enough to write about.
Yes, and well, no, it's already worth writing about, but I'm going to send you a hard test case that I've been struggling with for years, and I think you're making progress in it. That's what I'm really delighted about. But that's
I look forward to it
later tonight when I got some time.
Okay, thanks a lot. Thank you, Zaid. Talk to you again.
Yeah, it was a pleasure talking to you both.
Okay, bye.